Hi, this is Brian Fogarty, and this is a video for Chapter 11 of the book Quantitative Social Science Data with R, second edition. And in this video, we are going to look at carrying out multiple regression in R. This begins pretty far into the chapter. I chose not to do a video for bivariate regression, just because it's too sort of simplistic. The discussion in there kind of helps you understand how it all works, but then the real action is with multiple regression, so I decided to just get to it. Just get to the work here. All right, so I've opened up and saved a new R Markdown file here. I'm going to set the library path and the working directory. Okay, I already have this in here just so we could save some time without typing again. This is all stuff we've done before, and it is also in the chapter. So we're going to use here the SIMD data set. This is the 2020 Scottish Index of Multiple Deprivation. And we are going to do a simple multiple regression model where our outcome variable is percent depress, and we have three predictors: percent employment deprived, which is employment deprivation; percent overcrowded, which is housing overcrowding; and then our urban variable, which is just a dummy for urban or rural data zone. Okay, so we're just going to do some recoding of that just so it's in the format that we want. Okay, so let's carry this out. So we're going to save this as an object. You don't have to do this, and you could save it whatever you want. When I do regression, I tend to save things as like model 1 or model, and it's related to a specific thing that I'm doing. So we're going to save this as that's our object. And then to do a linear regression, an OLS linear regression, the function is just LM, which stands for linear model, or linear models. And we include our outcome variable first, so percent depress, and then tilde, and then we'll include our predictors. So we're going to do percent employment deprived plus percent overcrowded plus urban underscore FCT, and then the data we're using. So data equals SIMD. All right, so if we run this, we everything will get saved to the object model 1, but we actually want to see it. We don't want to use another step for it. So what we'll do is we're going to wrap the summary function around it. Okay, so that's all good. It looks good to go. Let's run it. All right, so I'm just going to pull this up just a little bit because there's a bunch of information that comes out. So most types of regression that we run, so here we're doing linear regression, but this is the case for generalized linear regression, which we'll look at as part of chapter 13. The output generally looks like this. It always kind of looks like this. What we'll do here is we're going to do a quick review of some of the stuff happening here. We're going to start at the bottom. So we're going to start at the end, work backwards in some respect. We're going to memento it. Or what's the new? Tenant it? Something like that. All right, so let's sort the F statistics. So this is a looking at sort of our overall model fit, if you will, and it is comparing our model to a model where the coefficients equal 0. I tend to like to talk about it as when we have nothing. So we have no predictors. So it's saying like, is our model better than a model with nothing, which should be a pretty low bar. It's not always, because it's susceptible to n, the number of observations, and as well as the type of data we have. So sometimes survey data with a small n can be tricky. And we're just looking here at this p-value. So we have the f statistic, and we could look this stuff up if we wanted to, but R gives us the value here. So we're just looking for, is it less than 0.05? It is, so that we say that our overall model is statistically significant, or our model is better than 1 with nothing. Right? Okay. The next thing we want to look at is this multiple R squared. Okay. This is a measure of how much variance is explained in the outcome variable based on our model. So we can convert this to a percentage and say, we're going to just play around with it a little. Let's say, so 65.6% of the variance in percent depressed is described or accounted for by our model. Okay, adjusted R squared, which talk about in the in the chapter more. Adjusted R squared takes into account the number of predictors we have, because R squared has this characteristic that as you add more predictors, it always goes up, regardless of if those predictors are providing any value. So adjusted R squared takes into account how many predictors we have. And so what we're really doing is looking to see like how close they are. Because if the adjusted R squared is way lower, then it could be there's some predictors that are really not contributing. But how we pick predictors when we're building these models really should be driven by theory and our substantive expectations, not just data mining. That's always a bad way to go. It's not always a bad way to go, but within most of the work we do in social science, it's not a great approach. All right, so here we see they're almost identical. This is about as good as it gets. I mean, adjusted R squared will never be greater than R squared. Okay, so that's considering the overall model. Some people get really hung up on this R squared stuff. It's just one measure. It's our overall model. I mean, usually what we care about is what's happening here, the effect of individual predictors. Okay, so we have 3 of them here. We have percent employment deprived, percent overcrowded, and then our urban variable. It looks a little funky like this because what this is this is the urban FCT, and then it's including the higher category. So it's including urban as the higher category. So the effect is urban versus rural data zones. Okay, so the first thing we should do for each of these is figure out which ones are statistically significant. Now, R, like a lot of different statistical programs, gives us redundant information about this. Let's go through it. All right. First, what we can do is just look at the stars. All right, we're going to work kind of backwards. So it gives us stars down here, corresponds to levels. Basically, with R, if our predictor has 1 of these, that means it's statistically significant. Okay? Now, we also have this column here. This is the p-value. We are looking to see whether or not the p-value is less than or equal to 0.05. Okay? And then we have the t-value. The t-value, we're looking, it's a little, so roughly 2. The absolute value, roughly 2. If it's minus or positive, it doesn't matter. So if it's 2-ish, that means it's statistically significant. It varies depending on the number of observations you have. All right. And then we can also use estimate and standard error. And so what you're looking here is the estimate, which is also known as a regression coefficient, is it twice the size of the standard error. All right, so let's work at this the other direction. All right, so we could say first, here are regression coefficients. Positive means there's a positive effect. Negative means there's a negative effect. And again, what we're looking for is the estimate, which is the regression coefficient, at least twice the size of the standard error. All right, if it is, then it's statistically significant. The t-value is attained by dividing the estimate by the standard error. So you're looking to see, again, if it's at least 2, the absolute value 2. And this is why it's the absolute value. Because you can have a negative effect. That means as percent overcrowded increases, percent depressed decreases, right? So that doesn't mean there's less of an, like it's less in terms of statistical significance. It just means that the effect direction is negative. All right. So again, t-value 2, absolute value, p-value 0.05, and then stars. So we actually have 4 different ways of figuring out whether it's statistically significant. They're all redundant, right? We just need one, really. So looking at this, we can see that all of the predictors are statistically significant. Okay. What we would do next is to provide a coefficient interpretation, where I have a bunch of this in here in the chapter, but we provide a coefficient interpretation, and then we provide some discussion, right? Like we think about, we want to know what the effect is, but we also want to be able to interpret it, but also discuss it so that people that don't know anything about doing regression can get an idea of what is happening. I'm going to not do the interpretation in this video just because I think it's fairly well covered in the chapter and it's nothing to do with R per se, right? Okay, so that is it for this video. Thanks for watching, and I will see you next time.